It's actually really great to be here. I think this is a fantastic workshop, and it's something that I care truly greatly about. So what I want to do today is talk about the emergence of highly transparent PVs. And I'm going to first start with just a very quick introduction to my group, and then I have actually quite a lot to go through. So the first thing we do in our group is actually to develop new materials and actually do molecular synthesis of organic, nanostructured, and exotonic materials. We then take those materials and try to understand how to grow them into films, how to control their crystal structure and orientation. And so we also do a lot of in situ diffraction, electron diffraction. And we do this with not only organic molecules, but also with inorganic materials and halide perovskites. We take those materials and that understanding, and we do a lot of different applications. So we convert light to electricity, solar photovoltaic. This is an example of a perovskite device over 20%, pretty standard now. But what I think we're probably most well known for is for converting devices, opaque solar cells, into solar cells that are completely transparent. We also do this in reverse, so we convert electricity to light. We do a lot of work in light-emitting diodes, both OLEDs, as well as next-gen nanocluster-based phosphorescent LEDs. And we've started to branch into new fields where we convert light into various kinds of medicine via photodynamic therapy. But the thing that we spend the most time on and are probably most well known for is this transparent PV work, and that's what I'm going to focus on today. And so I want to start off by talking about this idea, because I think we all kind of get the idea, but I think early on it was confusing to a lot of people. And if we want to make a solar cell completely transparent, where do we get the power from? And the answer lies in the photon flux. And if you're talking about a single junction cell, it's a solar photon flux that actually matters, because every photon is at most going to produce one electron. And so what we're going to try to do is harvest the invisible lights predominantly. We can harvest some of the visible and then predominantly harvest the invisible. And you can see with this plot that the majority of the spectrum is in the infrared, and there's still a small but substantial part in the ultraviolet. And I'll talk about both pieces of this. You can ask if, I took something like a traditional semiconductor like silicon, and I wanted to make it transparent. You have this somewhat severe trade-off of you can either make it absorb light, in which case it's going to absorb light through the entire spectrum, or you can produce power. So at the highest transparency levels, you produce very low power, and at the highest power levels, you produce the lowest transparency. So there's this very severe trade-off. And so we really were thinking about a way to overcome this trade-off early on at the beginning of when I first developed my lab. And we recognized that organic and exotonic materials are really the original quantum dot. They can create tunable resonances that allow you to create structured absorption. And if you tailor this into the right parts, you can focus on predominantly and selectively harvesting the invisible parts of the solar spectrum. And these are the first molecules that we use to demonstrate this kind of approach. Why is this possible? This is possible because of the molecular orbital nature of these molecules. Like I said, really the original quantum dot. So you think about the traditional band gap, the ground state to the first excited state, but you also, because of the separation between these molecular orbitals, you can open up additional transmission windows where you don't have a density of states, and you can transmit this light to allow visible light to pass through. In the interim of our very first demonstration, we've shown a whole catalog of these kinds of materials that can selectively harvest in the infrared, scanning from the shortwave near infrared to deeper into the near infrared, particularly with things like phthalocyanines, small molecules, as well as polymers. This is actually a polymer from Yang Yang's group, carbon nanotubes, as well as organic salts. And when we first started thinking about this was sort of the approach that was taken when we first started. It was to take an opaque cell and cut holes or make slivers of that opaque cell to let some of the visible light pass through, or to just take these kinds of semiconductors and make them ultra thin. And there's two trade-offs that you get with that. You not only get a trade-off with overall transparency level, but you also get a trade-off with color impact with some of these approaches. And so what our approach really allowed us to do was to focus on harvesting the ultraviolet and near infrared predominantly, and that allowed us to get to the highest levels of transparency while maintaining the highest level of efficiency simultaneously. So I'm going to talk about these different approaches, but I'm going to talk about the first design that we actually did. This is what kind of started the whole thing. So we designed a traditional organic photovoltaic cell where we took the active layer and it's selectively absorbing in the near infrared. And so it seems like very simple. Basically, the hard part is already done because we can just take the cell now, put a transparent electrode on it, and we'll basically have a transparent cell. And so we started playing with this design, and there's actually a number of challenges, and it's not nearly as simple as it looks. So the first thing is that we took indium tin oxide and made it the anode and the cathode, and that created a number of design challenges because we have essentially what should be the same work function on both sides, and so your voltage was abysmal. And so the first tricks we had to do to overcome this was to actually figure out how to set work function and create a work function offset. And we did that with metal oxide layers. The second thing that we found was that when we started making these devices, if we grew different thicknesses of just this transparent cathode, our performance varied wildly. So when we went from our control cell of 2.4% to our first transparent device with a thin indium tin oxide layer, we see there's some resistance in the forward current. Once we go a little bit thicker, that forward resistance essentially goes away, but then our performance is dominated by the thickness impacting the photocurrent. And so we increased the photocurrent and essentially the power conversion efficiency by a factor of 3 just with this one parameter. So it's not a simple device. There's a lot of complex optical interference going on, even though it seems like a simple transparent device. But nonetheless, with this simple optimization, we showed that we could take a 2.4% opaque cell, convert it to a transparent cell with 65% transparency and a power efficiency of 1.7. And so to put that in perspective, this is a snapshot of what was happening at the time, where we plot PCE versus average visible transparency. And all of these blue dots are basically these spatially segmented silicon or visible absorbers that are just made ultra thin. And so our first demonstration with this wavelength selective approach are these two red dots. And what's interesting about this is to even make this plot, nobody at the time was calculating average visible transparency correctly. This actually comes from the window industry. Nobody was calculating it correctly. Everybody was using an arithmetic average. And so we had to actually introduce this language and so that we were consistent and we weight the transparency with the photopic response of the eye. Since about 5 or 6 years later after that, this is the progress that's been made. And it's truly astounding to see what's happened since those first demonstrations. So the green ones are the wavelength selective approaches. The red ones with the green outer shell is our wavelength selective approaches that come from our lab and our company, Ubiquitous Energy. And there's a couple that I want to highlight here in particular. This point here, which was a certified device over 5%, 3 or 4 years ago, and another one over here, which is another certified device by Ubiquitous Energy, 9.8%. More recently, we have devices with similar performance moving ever upwards in the AVT space. And within the last year or two, there's a handful more that have emerged. When we started in this field in 2010, I made a prediction that everyone in the OPV world would be working on this, and I think many now are. So it's very exciting to see this kind of development and this kind of enthusiasm for these kind of devices. Now, one of the questions that arises when you look at a plot like this is how far to the top right in this space can we go? And so we looked at this very early on by doing a Shockley quasar detailed balance. If you take the theoretical limit for completely opaque cell single junction, efficiency limit's 33%. If you cut out all the visible light, the efficiency limit only drops modestly to about 21%. And if you want to harvest some parts of the visible light neutrally, you can get efficiencies anywhere in between. So you can get over 25% with like 50% transparency. You can then think about stacking these together with different transparent cells with different band gaps to make multi-junctions, which I think is something that you guys have recognized as critical to increasing the performance. And indeed, if you go this approach, you can make transparent cells completely transparent above 30%, and with a reasonable amount of transparency, even above 40, approaching 45%. So this really shows you the potential. In fact, if you take silicon, silicon gets more than half its power from the infrared. And that's why these efficiency limits are so high. Now, the key in what we did is to take the efficiency limit of the spatially segmented, this dotted line, black dotted line, and actually raise the bar. So by taking a wavelength selective approach, this changes everything. So even at 50% transparency, you effectively double your efficiency potential. And if you go to the highest levels of transparency, you practically increase your potential by like a factor of 10 or more. theoretically you increase it infinite. So this is the whole sort of game. The OLED world was disrupted by increasing the efficiency limits by a factor of 4, and this is, I would say, something analogous. So there's a lot of approaches that we take to really optimize these devices. The first tried and true method is we work on taking these small molecules and organic and exotonic materials, blending them together to overcome the bottleneck. I'm very glad to see Professor Gretzel here. He developed the dye-sensitized cell approach that overcame this exciton bottleneck well before everyone else figured this out. But nonetheless, bulk heterojunctions are starting to catch up. And this is something that we've used to show with those early materials that we can enhance the performance quite quickly. And in fact, that's the method that we've used to reach efficiencies close to 10%. The second approach we think about is actually measuring and designing exciton diffusion lengths. If we can just get a long exciton diffusion length, then we don't need to worry about complicated bulk heterojunction structures. So our exciton diffusion length can vary based on molecular structure, but things like crystal size and crystal orientation play a big role. I spent a lot of time developing methods to actually measure exciton diffusion lengths, and this led us to think about how to actually design longer exciton diffusion lengths. So that's another area. Another aspect is that these materials have anisotropic crystal structures, and if we can orient their crystals in particular directions, we can take advantage of those anisotropic properties. If you get the right orientation, you can think about higher mobilities and higher exciton diffusion lengths, which is what we see here in the black and blue curves. We can increase the photocurrent, but it also affects the HOMO level by adjusting the crystal orientation. And so you can actually deepen the level, increase the voltage simultaneously. And this example where we had crystallites standing upright versus laying flat, this was an example where we could just double the efficiency with the same material effectively. We do a lot of work on optical interference. This is critical to optimizing the performance, but also to the angle dependence, which I'm going to talk about later. This becomes particularly important when you're talking about tandems. And then the last approach we do is actually just synthesizing new materials to expand our catalog and our platforms of accessible materials. And that's where I want to talk about one interesting platform that I think is particularly surprising. And it's based on a cyanine salt. So this is a polymethene cyanine salt where we have a cation and a counterion. And so this is like sodium chloride, but now we can make the cation and the counterion both organic. And this has been used historically in like CDR recording media. And a number of folks have been playing with sort of variations of this, but we picked this particular one because the band gap was deep into the near infrared with very good wavelength selectivity. And we asked a simple question: what does the counterion do? We thought that if we change these counterions, we'd have an effect. At the time, people thought that this had no effect. And we thought we might start lowering the photocurrent because we might make it harder for hopping. But what we found was actually very surprising. We started to go to these weakly coordinating counterions, and we started to get better fill factor, and then better voltage, and better voltage, and better voltage. And in fact, our photocurrent didn't reduce at all. It actually went up, if anything. But our voltage just kept increasing without changing the band gap. These are all essentially around the same band gap. They have essentially all the same absorptive properties. And so what was going on was really stunning, but we took a material with a really modest voltage for its band gap and increased it to close to its theoretical limit for an excitonic solar cell. And just for reference, this blue point was that first demonstration. We liked that particular thiocyanine because it gave us such a high voltage. And so we didn't have to go and design thousands of molecules stabbing blindly in the dark to get the right voltage. We were able to just optimize the voltage. And it took us a while to figure this out, but it really came back to the counterion actually acts as a dipole induction layer that can affect at the molecular scale the HOMO level. And so we actually showed this with photoemission spectroscopy, that with the different counterions, we're actually independently adjusting the HOMO level. And so this is really crazy because usually you think about an ionization potential or a HOMO potential fixed for a material, but now it's an independent tuning parameter based on what counterion you're using. And so you can actually blend different salts together with the same cation, but different counterions, blend those together and actually get energy levels anywhere in between very precisely, and you get voltages between. So this is particularly important when you start to think about going deeper into the near infrared, and you have to balance electron energy transfer from the LUMO with the interface gap to maximize your voltage. Now you have a very sensitive tuning knob with very small band gaps to do that. And in fact, we've exploited that to show what was at the time the longest wavelength photoresponse in a small molecule PV or photodetector. And we had photoresponse out to 1600, and And we actually showed that we could optimize this and go out to even as far as 2000 nanometers, which opens up a whole broader catalog of molecules that we can think about not only for single junctions, but also for multi-junction cells. The other interesting part that comes about because of this counterion is its other effects. So with the parent compound, with iodide as a counterion, when you make this cell, it dies in about a day or two. And so you would think, well, this is just a bad material. It's not photostable. But it turns out that if you pair this with the right counterions, as you go to these more weakly coordinating, bulky, fluorinated type counterions, you can increase the lifetime by orders of magnitude. So these are all continuous one-son measurements at 65C, measured at max power point, and we see that the lifetime has gone from days to the best devices being having a lifetime over 10 years to T80. And so it took a material that looked like it was photo unstable and actually showed that it's very stable. And so this is really, I think, amazing demonstration and shows you what you can do at the molecular scale. The other thing that we have to start to think about when we're designing these devices is that when we integrate them into a building, they're rarely going to be at normal incidence. And so oblique angle dependence actually becomes even more important. And when we started to look at this, we wanted to analyze these different configurations and try to optimize this. But the first challenge that we ran into was that the transfer matrix models that we used to do these simulations were not accurate or correct, self-consistent at oblique angle. The polarization dependencies were wrong and the pointing vectors weren't correctly defined for oblique angle. They were all fine for normal incidence, but at oblique, it all broke down. And so the first thing we did in this paper, we actually went back and re-derived all these equations so that we could calculate the absorption, reflection, and transmission independently so that they're all add up self-consistently to 1 at all polarizations and at all angles. So this is just a confirmation of self-consistency. We then validated this model with actual device comparison. So we took a device and compared the model, and we see good agreement. And then we took that model and tried to optimize the roll-off performance. And this is just optimizing one parameter. We see that the roll-off can change dramatically as a function of incident angle, and yet the short circuit current density at normal incidence doesn't change very much. And so we then did a full optimization on all these different orientations and configurations. This is an example slice of this optimization space. And we went from this kind of roll-off to a roll-off that was much less severe while not reducing our normal incident photocurrent. And that difference between those two curves right here can lead to an increase in power production on a yearly basis of anywhere from like 20 to 40%. And that will depend on the location and orientation, but that's huge. And so angle dependence becomes really critical in these kinds of applications. It's something that we need to think about and is particularly important. So that first part of that talk was really focused on our first design based on a transparent PV that predominantly selectively harvests invisible light. And it's going to convert that light into electricity collected over a large area. We've actually developed other approaches, and I think one of the things you see from this conference is that there are a variety of approaches that can be taken. But we also wanted to show a complementary approach where we could do this optically. So instead of having to coat large areas of electrodes, we could take the same kinds of materials that selectively and predominantly harvest in the invisible, but then cajole them to emit in the infrared deeper. And then that glowing light gets trapped in a waveguide, guided to the edge where we mount thin strips of expensive solar cells. And the advantage of this kind of approach is that we can get to the highest levels of transparency because we don't have electrodes, so we don't have to worry about reflections and parasitic self-absorption. We also have a very low cost. The actual waveguide itself is where you embed the materials, and it's very low cost. And so this we see as really a complement because it really accesses a different transparency regime that's just not possible with the transparent PV. So we call this a transparent luminescent solar concentrator. So charge collection versus optical collection. And I want to talk about that a little bit. So we did the same kind of detailed balance and looked at the theoretical limits. And funny enough, if you look at these assumptions, you assume that your emitters are all 100% efficiency. You have no absorption emission overlap, meaning you have perfect step edge and delta function profiles for the absorption and emission. And you have a perfect PV mounted around the edge and 100% light trapping efficiency. Your efficiency limits actually reduce to that of a regular TPV. So your efficiency limits are 33% for opaque, 21% for completely transparent. And for those that are interested on the UV side, because we've talked a little bit about this, it's about 6 to 7% on the UV side. The practical efficiency limits, though, are a little bit different. So the practical efficiency limits on a TPV are around 15%, and we've been marching up towards that practical limit. On the practical limits for a transparent LSC, we think are closer to about 10%. So that's where there's a little bit of trade-off there. The practical limits on the LSC are going to be a little bit lower. The first demonstrations of these devices, we did both selective UV harvesting as well as near-infrared selective harvesting. And on the UV side, we developed these metal halide nanoclusters that absorb UV, downshift massively into the near-infrared, and have quantum yields between 80 and 100%. So pretty amazing materials. And then on the near-infrared side, we use a variety of the similar type of materials we use for the transparent PVs, cyanines and phthalocyanines, selectively absorbing the near-infrared and down convert. And these initial demonstrations all had efficiencies around 0.5% to 1%. Interestingly, this nanocluster UV side actually gets better as it gets bigger because there's so little absorption emission overlap. And so as the device gets bigger, the efficiency gets better, closer to like 1%. But what you can see is that we get very good transparent, very reasonable initial efficiencies, but transparencies of like 85% that can go up to 90. And so these were the initial demonstrations. This is one of our first devices that we made, just showing you. It's a couple inch by couple inch device. We plug it in, it's going to power the fan. And has very good optical clarity. We've since taken that idea and combined the ultraviolet component with the near-infrared component. It turns out that because the near-infrared, the ultraviolet absorber emits in the near-infrared in the same wavelength range where our near-IR is absorbing, we can't just blend them together. So we had to develop this structure where we actually separate them into two different panels. We call this a dual band concentrator, optically separate them with a low index gap. This can be either air or a low index polymer. We've done both and both work equally well. And I'm showing you sort of the best materials. We've optimized dozens to hundreds of these compounds for this kind of application. I'm kind of showing you a snippet of the best ones that we then took to optimize for for dual band devices. And this shows a little bit of the optimization where we can change the concentration of each of these independently, and you start to see the coloring that you get. Starts to yellow on the UV side, starts to blue on the near-infrared side. You combine these together, you get a soft green tint. Green and blue tend to be more acceptable tints for the window industry, and I'll talk more about that later on. But when we look at the performance, I'm showing the JV and EQE of these devices. I'll mention that this is pretty rare. Most LSC reports do not show JV and EQE, and this is something we're trying to change. But this is important for these devices to be comparable to any other TPV. And so if we look at these performance metrics, the UV only actually has a very good power conversion efficiency, close to 2% already. When we combine it with these near IR, we can go up to 3%. And so we now have 3% devices over a 2-inch by 2-inch area. We get good consistency between the integrated photocurrent from the EQE and the measured JSE, which is important. So good sanity checks. But this is the highest performance LSC of any transparency level. And it's also nearly half of the efficiency record of an opaque LSC. And to put it in perspective, we can plot it on these limit charts. And if we overlay it with the practical non-selective limit, we're actually surpassing that. So you wouldn't even be able to make a device like this out of silicon with this performance levels. Now, I'm not going to have time to talk about this topic, and I think our next speaker is going to maybe touch on some of this. But we've spent a lot of time thinking about how to take halide and halide perovskite semiconductors and take them from an opaque device to a completely transparent device. I won't talk too much about this. You can look up these papers here, but it comes down to this idea of band gap tuning on the UV side. And the reason that you might care about that, it looked like there was low photon flux, but there's high energy flux or higher energy in the photons, so that your voltage is actually very good. And if you look at the theoretical limits, if you get the band gap tuned right to the right band gap, you can get efficiency limits around 7%. So there is value, and I think the tandem UV with a organic near-infrared is a great approach. The last thing I want to touch on just for a minute or two, I know I'm running out of time, is to talk about testing. And that's because there's testing of transparent solar cells is actually more complicated than the testing of traditional PV cells. There's more metrics and things to worry about, and there's more ways to make mistakes. So the first metric that matters is power conversion efficiency, and this shouldn't come as any surprise, but early on, a lot of people tried to play funny games with monochromatic excitation or not reporting PCE in the same way for these kinds of cells. These should all be reported the same way, standard AM 1.5 illumination, and then you should measure the power that you actually output. And this power conversion efficiency should be defined exactly the same way for a PV or an LSC. This is really critical. One of the things that often is missing from this, masking is a very critical piece to make sure you have a very well-defined area. If you mismeasure your area, you mismeasure your JSC, you mismeasure your PCE by the same amount. Second thing is average visible transparency, which, as I mentioned before, we have to take from our transmittant measurement, which I'll get to in a second, and we calculate this based on the weighted photopic response. This metric is incredibly important to report accurately, and most people in the industry care more about AVT than they do about PCE. So if you mismeasure PCE by 10%, people tend to freak out, but they'll similarly freak out if you mismeasure your AVT by 10%. So it's important to get both of these measurements right. They're both incredibly critical. Additional to this, and maybe more supplemental, is the reporting of the color rendering index. So this is how good is the transmitted light coming through the window, and how faithfully do you reproduce your spectrum. In this case, your reference spectrum should be the AM 1.5 spectrum, and then your test spectrum is your transmittance or your reflectance multiplied by your AM 1.5 spectrum. Alternative to the color rendering index, the window industry also utilizes CIE color coordinates, A star, B star, so that's perfectly suitable. Different players use different metrics, and they kind of crosstalk on those, but one of the two of those are good. Another aspect of the JV measurement that's particularly important to recognize is that transparent PVs are intrinsically bifacial. And so what you put behind it matters. And so as a standard measurement protocol, the first and most important measurement is to do the measurement with a black matte backdrop behind the device so that you avoid the double pass. That is the standard protocol, standard measurement. You can add in additional measurements with different things behind it, but for comparison, we need that sort of black matte backdrop because it's not suitable to assume that you know what's going to be behind every window. And then the second one is in the measurement of the transmittance spectrum. A lot of people will use dual beam spectrometers to measure transmittance, where this is generally optimized for cuvettes in solution. And you'll see a reference beam. This reference beam is not useful for thin film measurements and should not be utilized. In fact, you should put nothing on the reference side, and you should only measure the absolute transmittance of your sample. You can then subtract off reflections separately by making a separate reflection measurement. But trying to put something on the reference beam to subtract off reflections is very difficult in a thin film device. So these measurements should be done in an absolute way where you take the entire assembled device and measure the transmittance through the entire assembled device. Lastly, you want to make sure that you do all the traditional PV measurement validations. So you want to do photocurrent integration to compare the integrated photocurrent from the quantum efficiency with your measured photo JSC. And then the last one, and this is a new one that you have to add in, is the photon balance. So if you take A plus R plus T, you want to make sure that you satisfy this. A is notably hard to measure, and so you can get this from the quantum efficiencies. So if we assume our internal quantum efficiency is maximum 100%, then our EQE can substitute for our A, and we can rewrite this expression, EQE plus R plus T has to be less than 1. And there have been a handful of reports that we've seen, and you can see still in the literature, that actually have numbers above this, which means that something has been mismeasured, either the transmittance or the EQE. But either way, it's problematic. So I'll just acknowledge pretty much everyone that's been in my group has touched on these projects in some way. I'll particularly note Chen Yang, who's worked on a lot of the solar concentrator work and is probably one of the best students I have. He's actually looking for positions right now, and he'll be defending his thesis later this summer. I also recognize the funding agencies, particularly the NSF, DuPont, BASF, as well as Ubiquitous Energy. that have mostly supported these projects that we've been talking about. And I'll leave up this quick summary, and maybe I can take a quick question or take questions after the session's over.
Thank you, Richard. Any questions? Okay, there is one question from Yannick Lafont. What is the main challenges that you see to switch from 2x2 inch to window size? And a second relating question is what consequences on the efficiency?
Sorry, I missed the second part of that question. What was the second part of the question?
What consequences on the efficiency?
What constraints?
No, the consequences. The
consequences.
Yeah.
Okay, well, let me talk about the first one. So, sorry, I've actually just forgot what the first question was.
What is the main challenge to go from 2x2
oh, yeah, 2-inch
to being
right, scaling up? So actually, one of the beautiful things about the solar concentrator approach is that once you've designed the materials, it's a very scalable process, and there's not a lot of roadblocks. You can use a lot of standard industrial manufacturing, extrusion, standard coating, spray coating. The challenge in the concentrators is actually in designing the materials to have the littlest amount of absorption emission overlap. And we often talk about increasing stoke shift, but stoke shift is not truly the right parameter because it doesn't tell you how much tail there is. It doesn't tell you about the breadth of the absorption emission parameters. And so spectra. And so really you want to have perfectly sharp like absorption cutoff and then a perfectly sharp emission cutoff. And you see ionic emitters that have like 5 nanometer emission widths. If you can get to there are essentially no challenges in my mind to scalability, to going to meter scale. We are already making foot by foot modules on the solar concentrators. At the same time, on the PV side, I think you have to recognize that there's scaling losses to charge transport, and so you have to whatever your lab scale is, you're going to lose a bit going into the module, and rule of thumb, that's usually about you lose about 25%, and we've already scaled our transparent PVs as well, and so I think that all of the challenges to scaling are solvable. I think you have to figure out the transparent conducting oxide, or you have to figure out good electrodes, and you have to figure out good designs. And maybe one of the bigger challenges that's less appreciated is actually when you're scaling up, you have to scale up in a way that maintains the aesthetics. And I'll talk more about this when I talk about Ubiquitous and their philosophy. But you can't have visual obstructions in the device if you want to get to those largest market applications. So that, I think, is one of the things that's maybe underappreciated and has to be prioritized to actually be successful. So I think it's important that we increase power conversion efficiency, and we're always trying to find better transparent conductors. Like those are just significant challenges across the field on the TPV side. But I think that they're solvable, and I think we're getting close to having these kinds of devices deployable.
Thanks, Richard. Very short question and short answer. What about the durability for building applications?
I missed part of that question.
Okay, this is my French accent.
Yeah.
What about the durability for the building applications?
Great question. Yeah. So I think at the research scale, we've shown a number of approaches where we can get lifetimes, in that sort of 10 to 20 year lifetime ballpark. So we feel very confident that that's not such a challenge. I think if you pick the wrong materials or use them in the wrong way, yeah, you can get very bad durability. But we at Ubiquitous, we pass all of the certification testing for IEC for the PV side of the testing, as well as the ASTM code for window testing. And those are really harsh testing. And so I think there's good promise to think that, we won't be the only ones to figure this out, but I feel like on the most part, we don't really worry about durability because we have so many formulations and device architectures that meet those specifications, that's actually still important and really critical. You have to pass those, but we have enough that we feel like that's manageable now. I mean, if you just spend some time thinking about it, you can actually solve this. Now, when it comes to the halide perovskites, I don't know. I mean, I think people are moving in the right direction and we're figuring this out from a thermodynamic standpoint, but we need to figure out the thermodynamic stability of these halide perovskites. And that side has not been solved yet. I think there's a lot of work to be done there. And I'm amazed because like our organic materials are way more stable than like inorganic quantum dots or a lot of these halide perovskites. And yet I think there's this persistent perception that organics are not stable, and I think that's just not true. And I think the OLED industry should be an indicator that that's not true also.
Thank you for this very, very optimistic point of view.